Hi, this is Nimla Rednam. In this video, we are going to discuss some special kinds of parallelograms. We are currently dealing with the third chapter, Understanding Quadrilaterals from NCERT textbook class 8. In the last video, we looked at exercise 3.3 that was dealing with parallelograms, and using different properties of the parallelograms, we solved the problems in exercise 3.3. Now here, there are few special cases of parallelograms. The first one we are going to discuss is the rhombus. Okay, so here you can see that they are right away starting with an activity of how to form a rhombus. So if you remember, we have done a similar activity for a kite. That is, we took a piece of paper and folded it, and then we drew these lines A, B and BC, which need not be of any particular, there is no rule that they have to be of equal length or anything, and then we got the kite. Now here we are going to do the exact same thing for rhombus. However, we have to make sure that AB is equal to BC in this case, okay? And then we obtain a rhombus. We'll come to the definition and everything. First, let's do this activity. So here I have with me a piece of paper, okay? And as we have done in the case of kite, I'm going to fold it, right? I'm going to fold it once, and then they're asking us to draw two lines, okay, AB and BC, but you have to make sure that they are of the same measurement. So in order to do that, what I'm going to do is, a simpler way of doing it is fold it one more time, okay. Now take this corner, right, which is the closed corner. All these are open corners, whereas this one is a closed corner. And what I'm going to do here is make one single cut, okay. So if I cut it like this, then what I have here is a rhombus, okay. So this is my rhombus. This is what they're asking us to do in the activity. So here by making a single cut after having a fourfold, we have made sure that all the sides of this particular quadrilateral are of equal length. So then we can say that the definition of a rhombus, the necessary and sufficient condition for a quadrilateral to be a rhombus is that all the sides are of equal length. Rest everything that follows are the properties of a rhombus, that it is also a parallelogram, it is also a kite, and so on and so forth. All the other properties are a consequence, but the necessary and sufficient condition for a quadrilateral to be a rhombus is that all the four sides are of equal length, right? So here first what I'm going to do is I will be drawing the diagonals, okay, and then we are going to discuss the properties of this rhombus. Join the opposite vertices, right? You get the diagonals, and then we'll discuss. Okay, first of all, they're saying that a rhombus is a parallelogram as well as a kite, right? Now, why are they saying that? Now, if you take this quadrilateral, clearly the opposite sides are parallel to each other. So, you can clearly see that the opposite sides are parallel to each other. That means that this rhombus, all rhombuses are parallelograms. Now, they are also saying that it is a kite. Why? Because we have seen that the definition we used for kite is that it has one of its diagonal as a line of symmetry. So you can see that this is the line of symmetry. In fact, it has two lines of symmetry. This is also a line of symmetry. Therefore, it is a kite as well, right? Now here, what are the properties? So clearly, all the properties of a parallelogram will be true for a rhombus, and all the properties of a kite are also going to be true for a rhombus, right? Now, additionally, what else can you say? Now here you will see that the as in for a kite, you know that the diagonals are perpendicular to each other. Here you can check that the diagonals are perpendicular to each other, right? Now here additionally, both the diagonals are bisected at the point of intersection of the diagonals, that is If I join these two vertices, you can see that they're meeting at the point of intersection. If I join these two vertices, the midpoint happens to be the point of intersection. That means that both the diagonals are bisecting each other perpendicularly in the case of a rhombus. Now we can prove the same thing using the geometry like we have done earlier, taking the congruency of triangles that lie within this rhombus. Let us do that. So here you will see that they have mentioned, we have already discussed this, okay, all properties of parallelograms and rhombus. And this is the additional property for a rhombus, that the diagonals are perpendicular bisectors of one another. Now, what is the proof they are using in order to prove it? If you are not, doing the activity, you will be considering these two triangles AOD and COD, right? So, if you consider AOD and COD, you will see that all the three sides are correspondingly equal. That is, AO is equal to OC because the diagonals bisect each other, okay, and OD is the common side, therefore it is equal, and AD is equal to CD. Why? Because in a rhombus all four sides are of equal length. Therefore, by SSS congruency, you know that these two triangles are congruent. If these two triangles are congruent, we can conclude that this angle is equal to AOD angle is equal to COD. Now these two form a linear pair. So if I assume each one to be equal to x, I know that x plus x has to be 180 degrees because it's a linear pair. That means that each one is equal to 90 degrees. Okay. So that is our geometrical proof, right? So this is about the properties of rhombus. So what are the properties of a rhombus? You have the properties of kite and the properties of parallelogram, and additionally you have the property that the diagonals in a rhombus bisect each other perpendicularly. So let's look at this example. They have given a rhombus RICE in this figure, and they're saying that find out x, y and z. Now here you can see that x is equal to 5. Immediately you can say x is equal to 5 because EO and OI are equal in measure because the diagonals bisect each other. Similarly, I can say that y is equal to 12, right? Because again RO is equal to OC, right? Therefore, y is equal to 12. Now, if you consider this triangle IOR, you know that this is a right angle triangle because the diagonals bisect each other perpendicularly. Now, in a right angle triangle, we know that by Pythagoras theorem, I can say that RI square is equal to RO square plus OI square. Okay. Square on hypotenuse is equal to sum of the squares of the other two sides. Therefore, I can say that this is equal to 5 square. RO is 12. So, let me write 12 first. 12 square plus 5 square, which is nothing but 144 plus 25, which is 169. That means that RI, I'm going to get RI as 13 centimeters. Okay, 13. Okay, they didn't give the units. So, this is about the solved example, right? Now, next, moving on to the next special case, it is a rectangle. Okay, now, what do we mean by a rectangle? Here, I can say that a rectangle is a quadrilateral with each angle is equal to 90 degrees. Each angle equal to 90 degrees. If you start from parallelogram, then the definition says it is a parallelogram with one angle as a right angle or 90 degrees. If one angle in a parallelogram happens to be 90 degrees, then it becomes a rectangle. Okay. So you can see here a rectangle is a parallelogram with equal angles. Okay. You can say a rectangle is a parallelogram with equal angles, or you can say it is a parallelogram with one angle equal to 90 degrees, because as a consequence every other angle will also be equal to 90 degrees. Or Okay, you can start with a quadrilateral like I said, and you can say that a rectangle is a quadrilateral with each angle is equal to 90 degrees. Okay, not one angle, you have to mention each angle equal to 90 degrees if you want to start the definition from a quadrilateral. Okay. So here they have given the proof of it by saying that if all angles are equal, then sum of the angles 4x is 360 degrees. Why? Because we know that sum of the angles in a quadrilateral is 360 degrees. Okay, and then each angle happens to be 90 degrees. Now here, being a parallelogram, it has all the properties of a parallelogram. Additionally, what do we have? Okay, additionally, the property of a rectangle is that the diagonals are of equal length. Now in a parallelogram, you remember the diagonals bisect each other, but they need not be of equal length. But in this case of a rectangle, which is a special case of a parallelogram, you have both the diagonals as equal. Now how do you prove that? Now what they've taken is, they've again, for the purpose of geometrical proof, they have taken these two triangles ABC and ABD. Okay, if you look at these two triangles, clearly AB is the common side, BC is equal to AD because these are the opposite sides, and this angle, included angle here, is equal because each of them is 90 degrees. Here this angle is 90, this is also 90. Therefore by SAS congruency, I can say that these two triangles are congruent. Now if they're congruent, I can conclude that the third side is of equal length, so AC is equal to BD. That means the diagonals are of equal length. Okay, and they're saying they bisect each other. This we already know because in parallelogram itself the diagonals bisect each other. So in a rectangle, naturally they are going to bisect each other. They're asking why. That is the reason, because we know that in a parallelogram the diagonals bisect each other, right? So that is about a rectangle. Now they've given a solved example. You have RENT as a rectangle and the diagonals meet at O. Find X if OR is given as 2x plus 4 and OT is given as 3x plus 1. Now here they have not given any of the measurements of either the sides or the diagonals, but they want us to find the value of X. How do we do this? You know that for a rectangle, both the diagonals are of equal length, right? And both the diagonals bisect each other. That means I can say that TO is equal to OR. Okay. So now they're equating these two. 3x plus 1 is equal to 2x plus 4. And if you simplify this, take all the, you take all the variables to LHS and all constants to RHS. You get 3x minus 2x is x and 4 minus 1 is 3. So the answer is x equal to 3. Okay, that's the solved example. Next, coming to the third special case, it is a square. Now, what is a square? It is a rectangle with equal sides. Now, in a rectangle, you don't have all the four sides as equal, right? So, but in a square, you have all the four sides equal. So, additional criteria for a rectangle to become a square is it has equal sides. All four sides are equal. Or if you want to start with a quadrilateral, you can say that a quadrilateral, okay, which has all the four sides as equal and each angle is equal to 90 degrees is a square, right? So now here I have, it has all the properties of a rectangle because you're starting the definition from the rectangle, right? And then you can say that here additionally the property is that the diagonals not only bisect each other, they're perpendicular to each other. We are going to prove it geometrically, right? How do we prove it? So this is the property that the diagonals of a square are perpendicular bisectors to each other. So in a rectangle, you know that the diagonals are of equal length, but they need not be perpendicular, right? In the rhombus, we have seen that they need not be equal to each other, but they are perpendicular bisectors of each other. For a square, the diagonals are equal in length and they are also bisectors of each other, and also not just bisectors, they are perpendicular bisectors of each other, right? So that's about the, so they have given a simple activity here. where they're saying take a square sheet and fold along the diagonals and then check all these three properties regarding diagonals. Let us do that quickly. So here I have with me a square sheet of paper, right? You can check that all the angles are 90 degrees. Now we are interested in the diagonals, right? So here I'm going to fold it in order to get the diagonals. Okay, this is one diagonal and then fold it here. You'll get the second diagonal, right? So these are the diagonals. So let me draw. I need a bigger scale. 1 second. So here, okay, now the diagonal is visible, clearly visible, right? So these are my two diagonals. Now let's check that they are perpendicular to each other. Okay, how do we do that? Using your set square, you can clearly see that these are perpendicular to each other. The diagonals are perpendicular. Do they bisect each other? Yes. How do you check that? You make the opposite vertices coincide at this point and you check the midpoint. Okay. Now this is my midpoint. If you open and see, that is nothing but the point of intersection of the diagonals. Again, you can do the same thing for the other diagonal. You make sure that the opposite vertices coincide. Okay, make a crease, find out the midpoint by folding method, and it happens to be the point of intersection of the diagonals. That means that the diagonals bisect each other perpendicularly. Now, are the diagonals of the same measurement? You can measure and check. Okay, if you see, the diagonals are going to be of the same measure. Okay, so you can see that here I have got 8.3 and here I've got the same measurement here, 8.3, right? So you can say that the diagonals are of equal measure, right? So this is the activity that they have mentioned. Now if I have to prove it geometrically, what are we going to do? Here you have got, what are the three things about the diagonals? We are saying that the diagonals bisect each other, that you can conclude from the fact that every square is a parallelogram. And now the diagonals are of equal length, that you can conclude from the fact that every square is a rectangle and in rectangle diagonals are of equal length. Now what about the fact that they are at right angle? So for that, what you're going to do is you consider these two triangles AOD and COD. Now here this is equal to this and this is the common side and this side is equal to this side because diagonals bisect each other. So using SSS congruency, okay, you can say that these two triangles are congruent. That means that again this angle is equal to this angle. Now these two form a linear pair. That means that each of them is equal to 90 degrees. You remember we used a similar proof for proving that the diagonals of a rhombus are perpendicular to each other, right? So this is about square. So with this, we have come to the end of this special cases of a parallelogram. And we have seen that it's very important that you understand what is the basic definition. By basic definition, what I mean is what are the necessary and sufficient conditions for a quadrilateral to be so and so, right? So that becomes your basic criteria. And then we look at different properties that we can conclude, that we can, derive from this definition of a particular case, right? So, and how do you arrive at these properties? You can either do them by activity. That way is for you to make for you to understand these quadrilaterals more intuitively and make sure that you remember them very well. Okay, and also it's equally important to prove these using geometry, because in the exam, if they ask you prove that for any square all the two diagonals are of equal length and they are perpendicular bisectors and so on. If they say ask you to prove, you cannot do an activity in the exam. So it is equally important for you to understand the geometrical proofs of this. And as you have seen throughout the entire chapter, whatever proofs we have done, we have been using congruency of triangles, right? So you have different congruency axioms, SSS, SAS, ASA. We have been using these congruencies for our proofs, to prove the different properties of the quadrilateral. So in the next video, we are going to be doing exercise 3.4.